Okay, I want to begin by thanking the organizers for inviting me. It's really a pleasure to be here today and speak to such a diverse audience that I can speak the same language to. So I think it's going to be a very fruitful exchange of information. I come from the University of Maryland, Joint Quantum Institute, and today I'm going to talk to you about some of the work we do with quantum dots and photonic crystals. I think you already heard a lot about it. Kai did an excellent job of introducing the field, so my job will hopefully be easier. This is happening because of the HDMI cable. That is supposed to be an atom. So what our group is interested in is interactions between atoms and photons. And usually the conventional reason people will say that they're interested in it is because of applications like quantum networking, where you want to use atoms as quantum memories and distribute information using photons as ideal information carriers. But there's an interesting duality to this picture, which is that just as photons are good for creating connections between atoms, atoms are also very good nonlinear media that create interactions between photons. And this goes back to some real pioneering work by Dwan and Kimball that has, motivates a lot of the things that we are interested in. And so this is not just a good way to exchange quantum information, it's also a good way to make large many-body interactions if you can control these systems sufficiently well. Now, I should admit, in my group, we don't use real atoms. We use artificial atoms called quantum dots, which are semiconductor nanostructures. Atoms are very nice to use, but we're just not very good at them. There are people at the Joint Quantum Institute who do a much better job at it than we do, and I'm sure we can exchange some ideas at some point, but in the current situation, I've been told that if I bring my 9 Tesla magnet anywhere near their labs, they'll be held to pay. So right now, I'm sticking with quantum dots. So these are small semiconductor nanostructures. These dots are indium arsenide quantum dots. Each one of these little specks is a small indium arsenide island surrounded by gallium arsenide. And due to a very fortunate overlap of the band structure, the dot behaves as a trap for both electrons and holes. So for the most part, we like to think about these nanostructures as effectively little artificial atoms. And basically have discrete energy levels that can be controlled and manipulated in the same way that real atoms can be controlled. So why are we interested in quantum dots? Well, first of all, they're robust quantum emitters. We have worked with the same quantum dot for over 2 years sometimes, so they really can make good, stable, long devices. There are a lot of ways to store quantum coherence, quantum information in them. Bright excitons, spin, dark excitons. I'll speak about some of these in my talk. But most importantly for us, the dots are already embedded in a solid matrix. So we already have them trapped in a solid. We don't have to use atom trapping technology, which really simplifies things for us. And also, fortunately, that matrix is a high index material. Gallium arsenide has an index of refraction of 3.6. So simply by patterning the surrounding substrate, we can make nanophotonic structures that are directly coupled to quantum dots. And that gives us a really interesting situation where we have both atoms and photons guided, embedded on a chip, and we can create strong interactions between them. And that's very fortunate because for a lot of the applications that I kind of roughly alluded to at the beginning, the requirements for interactions are very, very strict. It's very, very, very challenging. First of all, typically we need one atomic memory, in this case a quantum dot, to interact with a single photon. So we need to get this at a single atom, single photon level. But that's not enough. We can't just be able to turn on the interaction and leave it. We have to somehow be able to control the interaction. So somehow turn a knob that turns them on and off in a controllable way so we can actually drive the system into some useful state. And so in this talk, so the first part, how do we get these interactions? Well, you heard a lot of really wonderful work in circuit QED in the first session. And in that system, you can get very strong interactions, even in a 1D structure. But in optical frequencies with atomic systems, it's very, very difficult, inconceivable how one can get interactions between a single atom and a single photon without using some sort of optical cavity. So typically, you need to put the atom or the emitter in a cavity. And whenever you do that, there are 3 important parameters that will dictate the interaction that you will see. One is the coupling strength, which is the coherence term that corresponds to the unitary Hamiltonian evolution of the system. And the other 2 are the decay of the dipole and the decay of the cavity, and these are decoherence mechanisms. They tell us how fast the external environment destroys the coherence of our system. And in the dot systems that you're going to hear about from me and you heard about from Kai, the cavity decay rate is the dominant decoherence mechanism. We are particularly interested in the so-called strong coupling regime that you heard about, where the coherent term starts to dominate over the incoherent interactions. And so in the strong coupling regime, if I excite the atom and I allow it to interact with the cavity, it'll coherently and reversible exchange energy in a process known as vacuum-Rabi oscillation. So in the time domain, this will lead to a sinusoidal oscillation in the excitation of the atom and cavity. There's also a frequency domain picture, which is that of vacuum-Rabi splitting, where the atom and the cavity will split into two new resonances called polaritons. This is very similar to the bonding and anti-bonding states in chemistry. And so these are two equivalent pictures, and in this talk I'll exploit both of these pictures. But I guess the first question is, how do we get into the strong coupling regime? And for that, we note that G, the coupling strength, is inversely proportional to the mode volume of the cavity, and the decay rate is inversely proportional to the quality factor. So to get into the strong coupling regime, we need to find cavities with high quality factors and small mode volumes. In our group, we use these photonic crystal cavities that you heard about in the previous talk. We basically take a thin slab of gallium arsenide and we drill through electron beam lithography a periodic array of air holes into the slab, and we intentionally remove some of these air holes. That creates a defect in our photonic crystal, and this defect is where the light is localized, because if I have light bouncing around here, if it tries to escape in the in-plane direction, it sees a periodic index of refraction in any direction it goes that's reflected back to the defect. So there's no modes for it to couple to because it's within the band gap of these Bragg mirrors. In the out-of-plane direction, we rely on total internal reflection to confine the light. So this combination of Bragg reflection and total internal reflection is what we use to get three-dimensional confinement of the photon. And you can see that from the simulations. If you just take electromagnetic calculations of the structure, you'll see that the mode is very well confined into this defect region. Mode volumes of 0.8 times a cubic wavelength, so we're getting close to the diffraction limit. And if we measure the cavity Q, we can see Qs as high as 30, 40,000. These, I have to admit, are hero devices. We don't routinely get this. Routinely, we achieve about 15,000, but it's usually within that range. And that's good enough to get into the strong coupling regime. We can see that by simply taking our cavity, shining light from the top, and just scanning across the cavity with a tunable laser and measuring the reflection spectrum. This is a measurement of the reflection spectrum as a function of temperature. We have this bright thing here is a cavity mode. And you see that as we increase temperature, something weird happens here. We slice this cavity mode in half. What's happening here is there's actually a quantum dot that as we raise the temperature tunes across the cavity mode. And normally, if it wasn't coupled, the resonance would just walk right over the cavity mode. But you see, we see this anti-crossing like behavior. That's the signature of strong coupling. And here at around 39 Kelvin, we see the vacuum-Rabi splitting, which is the signature of the strong coupling regime. Now, this isn't new. This strong coupling, even with quantum dots in photonic crystals, was observed as early as 2004, and with atoms and other systems, it was observed even earlier. So this isn't groundbreaking. But as I mentioned, the real question is, so we can create these strong interactions. How do we coherently control them? And in this talk, I'm going to give two examples of coherent control in this strongly coupled regime. One is what I call light-matter quantum logic, and the other is coherent control of vacuum-Rabi oscillations. So let me start with the first part. Light-matter quantum logic, basically, we know that all computational devices that we use today are composed of a series of elementary operations called gates. This goes way back to the very famous Shannon theorem, where he showed that this is not the Shannon theorem of cryptography. This is his PhD thesis, where he actually showed that all logic operations can be decomposed into fundamental basic elements that are complete. And in quantum information, we have an analogous situation where we have universal quantum gates which we can construct any quantum logic, But in quantum information, we end up with a slightly different situation, whereas in this case, almost all the inputs and outputs of our gates are electrical voltages. A lot of times, in this case, we have to use signals from vastly different material systems. We may have to take an atom, a signal that's stored in an atomic qubit, and couple it to a photonic qubit. And so that puts us in a much more interesting and maybe more difficult situation. So one of the probably the most fundamental complete quantum gates in quantum information is what I refer to as a quantum transistor, which takes as an input an atomic and a photonic qubit. So this is a general concept. The idea is that let's assume this quantum dot has 2 qubit states. I haven't told you yet how I'm going to do it. I'll show it to you later. If I put the dot in one of these quantum states, this device should take the photon and send it to port A. Port A is an abstract port. It could be polarization. It could be different fibers. Could be many, many different ways. If I move the dot to its state 1, then it will instead send the photon to port B. That's the basic idea. So it's really just a basic switch. But instead of a gate voltage, we're using the state of the dot. But there's an important difference between a regular switch, like a light switch, and this one, which is that, of course, the dot is a quantum system. So I can put it in a superposition state. And if I then implement this operation, I should get this kind of strange case where the photon splits into both ports, and what I end up with is an entangled state. And the crucial distinction between the regular classical transistors in our computer and what this thing does is this phase preservation. That's the crucial part of the system that we have to maintain in order for this to be a quantum device. And the important point is that the strong coupling regime allows you to precisely implement this transistor action. So let's pretend again for now that my quantum dot has the following level structure. It has 3 levels, 2 stable levels that I can use as qubit states plus some excited state. Only one of these qubit states, in this case qubit state 0, is coupled to the cavity through this resonant excitation to the excited state. So if I'm in qubit state 1, I'm completely decoupled from the cavity. In this case, the cavity shows just a simple Lorentzian transmission spectrum on resonance. If I send a photon, I expect it to completely transmit through the cavity. That's just simple linear optics. But if I transfer the dot to state 1, now I can strongly couple. In this case, I expect to see vacuum Rabi splitting. Now, my photon, there's no response at the original resonant frequency of the cavity. So instead, the photon reflects. So I can use the state of the dot to control whether the photon reflects or transmits. That's how I can get the transistor action. And hopefully, if there's no energy left in the system, this should also preserve quantum coherence. And so how do we do it with a quantum dot? Well, it turns out that a quantum dot is, although I kind of said at the very beginning, well, a quantum dot is kind of like a 2-level atom. The excitations of a quantum dot are more complicated, fortunately. We actually have some energy levels, more complicated level structure that we can exploit. For specifically, a quantum dot excitation is composed of an electron and a hole, and each of them have a spin. And there's 2 ways in which the spins can combine. They can be anti-aligned, so you can have electron spin up and a hole spin down, or electron spin down and a hole spin up. These correspond to plus minus 1 angular momentum for the complete exciton of the system. And normally we don't see these 2 so-called bright excitons because they're nearly degenerate. But if I crank up a magnetic field, I can intentionally break this degeneracy. Then I can resolve them spectrally. And now if I give it just the right magnetic field, I can actually make one of the transitions resonant with a cavity, and that gives me this kind of qubit in a cavity system where one of the bright excitons it can be used as a shelving state or a qubit state, and the other one is used as a strongly coupled excited state to the cavity system. And so we went ahead and tried to implement this quantum transistor using this level structure. But I should say that the gate that we implemented is a little bit different from the simpler one that I described to you before. It's actually more along the lines of the very original ideas proposed by Dwan and Kimball, because we have a single-sided cavity, not a double-sided cavity. We actually have a DBR underneath our photonic crystal that only allows light to reflect up when we send a laser pulse. So that means the photon has nowhere else to go. If I reflect a laser pulse, it can only reflect back. But there is a difference between when the photon is resonant and detuned from the cavity. So if the quantum dot is in the ground state, where it's strongly coupled to the cavity, then a photon will reflect with a zero phase shift. It actually just reflects off the front surface of the device. But if I, say, use a bright laser pulse to shuffle the dot state to this bright exciton -1 state, now I'm decoupled from the cavity. A photon can couple to the cavity and come back out. That gives it an additional pi phase shift. So this basically, so instead of either transmitting or reflecting the photon, we imprint a phase on it. But fortunately, we can directly access that phase using polarization interferometry. And there's a convenient way to do it in photonic crystals, and we do it by utilizing the fact that the cavity has a well-defined polarization direction. Specifically, the cavity mode is polarized in the direction that is orthogonal to the rho defect. This is the x direction. So if we send a photon that is 45 degrees rotated to this axis, then if the quantum dot is in the ground state, this component, which couples to the cavity, doesn't pick up any phase shift. It remains with the same phase, and when it adds with this uncoupled component, the polarization of the photon doesn't change. If we transfer the state to the minus state, however, this guy picks up a pi phase shift. It reflects across the origin. And now, when you add these two components up, the polarization is actually rotated 90 degrees. So the phase shift is converted into a rotation of the polarization. Another way to think about it is we convert this quantum phase gate into a quantum dot photon C naught gate. And so we went ahead and did that. In order to implement this gate, we have to do everything with fast pulses because we need to do it fast compared to the decoherence time of all of our qubit system. So we can fortunately prepare the qubit state with one short picosecond optical pulse into any superposition of its two qubit states, and then we can probe the system with a second probe and just look at whether it transmits through a polarizing beam splitter, and that will tell us whether the photon incurred any polarization rotation. And so this is the results. When we put the dot in the ground state, we see that there's a suppression. We see this kind of vacuum Rabi splitting, and on resonance, the photon is there's an inhibition of the transmission of the photon through the polarizing beam splitter. If we move the dot to the minus state, we instead see a much higher probability of the photon transmitting through the polarizing beam splitter. The contrast is not perfect due to the finite bandwidth of the pulse and the finite cooperativity, but we definitely get about a 50-60% change. And so that kind of demonstrates part of this quantum operation. It demonstrates the fact that we can flip the photon polarization. And the question now, now we should be able to do a lot of wonderful things, right? We should be able to entangle a photon with dot. We should be able to create entanglement between different photons. But and actually, in trapped after our work, there was a sequence of results using trapped atom cavity QED, where actually you showed very advanced quantum logic operations. There was work by a Harvard group here where they showed a quantum phase switch, and really nice work by the Rempe group in the Max Planck Institute, where they actually entangled two photons using this gate. So we should be able to do something like this. Why not? Well, unfortunately, it turns out that this bright exciton qubit sucks. It's a terrible qubit. It has a coherence time of about 100 picoseconds, and the reason is because it's an excited state. It can radiatively recombine, and that ultimately puts a limit on our coherence time, and so we don't have a lot of time to do anything interesting. So a much better qubit, as was described in the previous talk, is not to use these optically active excited states, but to use charges to charge the dot, to add a single electron to the dot, and that electron brings along with it a spin degree of freedom. And that spin is a really nice coherent system. We have two stable ground states, and they're coupled to two excited states called trions. So we now can actually we can actually work with a nice stable two-level system. There's pioneering work by the Yamamoto group. They showed that this qubit has T1 times of greater than 1 millisecond, T2 times longest that have been shown so far is 2 microseconds. It's really still an open question why there's such a big difference between the T1 and the T2. That's work in progress. There is still some hope. Many of us hope that we can actually do some sort of dynamical decoupling to bring this way up to the millisecond regime, but that's still work in progress. At the same time, we can very quickly manipulate the spin using optical coherent control. If we use a fast kind of this optical detuned Raman transition, that creates an effective Larmor precession of the spin, so we can actually prepare the spin state on picosecond timescales. So what does it look like when we put one of these dots in a cavity? Well, in our case, we charge the dot by random doping. There's enough crap in the MBE machine that grows these structures that once in a while there's a donor impurity and it adds an electron to the device, and we can tell that from the spectroscopy. This is a fluorescent spectrum where you have a cavity spectrum and a nearby quantum dot. And what we do is we crank up the magnetic field, and we start to see that the quantum dot has this Zeeman splitting. And you crank it up even higher, and then you see 4 optical transitions corresponding to these 4 different possible radiative transitions in the system. And if you go even higher to about 6.6 Tesla, now this transition sigma 1 becomes resonant with a cavity. And so we have a very similar situation to what we had before. If I'm in the spin up state, I'm resonant with the cavity. If I'm in the spin down state, hopefully all of these transitions are detuned. And so I have it now, and now I have it in effectively a lambda system, a nice stable lambda system, as opposed to the V system that I had before that's not stable. And so the first thing one would like to see is a spin-dependent cavity reflection spectrum. So to prepare the spin, we optically pump by turning on a laser on this transition. If the dot is in this spin state, it gets excited, and then eventually it'll release a photon, end up in the other spin state, and there it will hopefully stay for a long time. And so we optically pump, then we measure the reflection spectrum, and we see just a bare cavity reflection because we've basically pumped it into the state where the dot is detuned from the cavity. But if we optically pump the other transition, push this dot into the spin-up state, now we see this strongly coupled spectrum. If you're wondering what this blip is, it's the other transition. It's the slightly detuned transition. It's completely expected, and this solid line, which is a theory, also reproduces it. Okay, so that tells us that we have a spin-dependent cavity reflectivity. By flipping the spin, the cavity reflectivity will change. Now, can we actually control this spin? And here's how we achieve coherent control. First, we use an optical pumping pulse to prepare the spin in a well-defined spin state and spin up. And then we use 2 detuned pulses to rotate the spin. The first pulse will rotate the spin onto the block sphere. At this point, the spin is going to start to precess around the block sphere due to the magnetic field. If we wait just the right amount of time, it'll do an integer number of precessions. Then the second pulse will flip it to the spin down state. And then we can probe to see what the reflectivity looks like. However, we can do the same thing, but instead of waiting an integer number of precessions, we can wait an integer plus 1/2 number of precessions. We end up on the other side of the block sphere. Now we rotate the spin to the spin up state. So we should see a drastically different reflectivity when we have this situation versus that situation. And indeed, that's what happens. We simply probe the cavity reflectivity. We increase the delay between the pulses, allowing the spin to go through its different rotations. And we see a clear signature of electron spin resonance in the system. But it's being probed in a very interesting way. It's being probed by looking at how much light reflects from the cavity. And you see, we measure the T2 star time. It's about 1 nanosecond. That's what you expect if you only do Ramsey. In order to get the 1 microsecond lifetimes that have been reported by the Yamamoto group, we would have to do a spin echo or Han echo. We haven't done that yet, but we expect that if it behaves like most of the dots, it should get up to these coherence times. There's another. So there's an interesting complementary effect here. What you saw in the previous results was that the spin determines whether a photon polarization gets flipped. But there's a duality to this process. Suppose that I do the same thing. I optically pump the spin down state, and now again I have 2 pulses. So you rotate to the block sphere, wait an integer number of rotations, then the second pulse rotates to the excited state. Now, let me inject a photon in between these two optical pulses. What happens if a photon reflects off the cavity between these two pulses? Well, the first pulse will again rotate you to the Bloch sphere. You make an integer number of rotations, but remember that photon reflection, which implements this Dwan-Kimball gate that is so important for our work, it gives you another pi phase shift. What does a pi phase shift do? It rotates you another 1/2 rotation across the Bloch sphere. So now I would rotate to the spin-up state. What does this mean? It means that just like a single spin can flip a photon can flip the spin. And so how do we see that? We do the same Ramsey interferometry. So this is the same Ramsey oscillations you do before. And then we compare it to the case where we inject a weak coherent field and we condition our Ramsey measurement on detecting a photon in this probe pulse. And when we condition it, we see a 90-degree phase shift in the Ramsey fringe. So this tells us that not only are we able to, this is actually a coherent process. When a photon reflects, it doesn't scramble the phase of the spin. It gives it a very well-defined 90-degree phase shift. And so this is a kind of nice complementary measurement that shows that this operation is actually a phase-preserving process. Okay, so let me move on to the second part of my of the talk. So far, everything I've told you about. By the way, how much time do I have?
15 minutes.
Oh, okay, good. So everything I've talked about so far we've just been looking at this in the frequency domain. So if we have a dot strongly coupled to the cavity, we get the vacuum-Rabi splitting. If not, we just have a bare cavity spectrum. But can I achieve coherent control in the time domain? Well, what does that even mean? So let me give you an example of how one could try to coherently control the system in the time domain. Suppose that I have a dot coupled to a cavity, but the dot is frequency detuned, and I excite the dot with a right laser pulse. No energy will be transferred to the cavity because the two systems are decoupled due to the detuning. Now, let's suppose on a time that is short compared to the decay rate of the dot, I could change the resonance of the dot very quickly, make it resonant with the cavity. Now the two can couple, and I can start to see vacuum-Rabi oscillation. So energy will transfer from the dot to the cavity. If I wait, we should keep on going. The vacuum-Rabi oscillation should just continue. You send it to the cavity, then reabsorb it to the dot, reabsorb it to the cavity. But suppose that when I get perfect transfer, I quickly detune the dot again. What does this do? It coherently transfers one photon from the dot to the cavity. And so this is a really versatile way, in principle, to control the photon field in the cavity. I can cascade this process. I can put 1, 2, 3, 4, 5 photons. As a matter of fact, it's been shown it's even possible that I can dial in whatever photon wave function I want in the cavity. So I could create any arbitrary superpositions of photon number states I want by repeating this process. You want a squeezed state, you dial in a squeezed state. You want a Schrodinger cat state, you dial in a Schrodinger cat state. And what's really amazing is that it has actually been done with circuit QED. The Martinez group showed what to me and probably anyone working in atomic cavity QED is amazing results. They loaded up to about 6 photons in the cavity, and they developed this feedback approach where they were able to dial in arbitrary 6-photon wave functions. And so and that's because clearly in circuit QED they have fantastic cavity QED parameters. But in optical frequencies this is much harder. And one of the main reasons is we're dealing with much faster dynamics. In our case, we're dealing with picosecond dynamics. So we need a way to actually tune the dot on and off resonance with the cavity on picosecond timescales. And that's very challenging. But a while ago, we kind of randomly stumbled, I should say, onto one possible candidate, which is cavity-enhanced AC Stark shift. So if in this measurement, we're basically tuning a laser across the cavity resonance, and what you're seeing here is kind of the spurious back reflection from the laser. And when the laser hits the cavity resonance, there's 2 dots here, and you see that their resonance shifts out. It shifts away from the cavity. What this is an AC Stark shift, and it's a very large AC Stark shift because the cavity is really enhancing the intensity that the dots see. And so now we have ability to tune the dot optically, tune it with light. And we can tune it on time scales that are on the order of 5 picoseconds, cavity lifetime. So we're starting to get onto the time scales where we might actually be able to tune a dot in and out of the cavity within the time scale of a Rabi oscillation. But there's a problem. The AC Stark shift always tunes you away from the laser. So if I have one cavity mode, I cannot use the same cavity mode to get both an AC Stark shift and to strongly couple. And it's even questionable what it would mean to tune, to look at strong coupling when I'm blasting the cavity with a bright laser. Fortunately, we came up with a solution to this problem. Instead of using just a single cavity, we use a more complicated structure called a photonic molecule. Photonic molecule is composed of 2 cavities that are evanescently coupled to each other. And because their evanescent fields overlap, the photon can hop back and forth between the 2 cavities. What you end up with is these these coupled states where the 2 cavities are in phase or out of phase with each other, and the 2 modes are shifted by the tunneling rate between the cavities. So this is kind of the photonic analogy to a molecular bonding. And so that creates a very interesting situation for us, because now instead of 1 cavity mode, we have 2 cavity modes. And they're detuned by quite a lot. This is a spectrum as a function of temperature, and this is one of the coupled modes. This is the other coupled mode. And as we increase the temperature, you'll notice here there's a quantum dot that tunes across this cavity mode, and it anti-crosses. What does this mean? It means that here we have this quantum dot strongly coupled to this cavity mode, and we have the second cavity mode that we can use to AC Stark shift it in and out of the cavity resonance. And now we can try to do that on very fast timescales. And so the first thing we did was we simply just tried to see if we could just, with a continuous wave laser, Stark shift the dot onto the second mode. And so this is the measurement here. We're tuning the laser across this lower energy mode, and what we see is that when we hit resonance, the dot shifts, starts to transfer energy to the higher energy cavity mode. And so yes, we can indeed use light to tune the dot onto the cavity resonance. So now we have to do it with really fast pulses, because our decoherence times are going to be on the order of picoseconds. So the first thing we can do is excite a cavity, put some light into it, and then use a very fast Stark shift to try to push the dot onto cavity resonance, wait a little bit, detune it, and then we see if the dot emits photons. And so this is the measurement we get. What we're measuring here is the emission of the dot as a function of the delay between the excitation pulse that puts light in the cavity and the Stark shift pulse. And when the 2 happen at approximately the same time, well, not approximately, within about 14 picoseconds of each other, then we see bright emission from the dot. We always see some bit of emission from the dots due to incoherent Raman processes that feed light from the cavity, but we can see a very sharp emission only when we've put some light into the cavity. We can do the reverse process. We can put light on the dot, we can then Stark shift it to the cavity, and we can try to see if emission comes from the cavity. And indeed it does. The spectrum looks a little more complicated than what you saw before. What you see is this oscillations. These oscillations are actually, they're not a cavity effect. This is called a perturbed free induction decay. It will happen whenever you take an emitter, excite it, allow it to decay, and then perturb its free induction for a short amount of time and allow it to continue to decay. You can see it with bare quantum dots. So I don't have too much time to explain this in details, but it's a well understood effect. The bottom line is here, if we pick the timing right, we can indeed transfer energy from the dot to the cavity. However, this energy transfer, so far, I haven't shown you any coherence. This could be just any kind of incoherent process that could be making this transfer. How would I demonstrate coherence? Well, the ideal way to do it is I would basically put the dot on resonance with the cavity, and then I would increase the amount of time that the dot is allowed to interact with the cavity, and what I should see is that the excitation goes from the dot to the cavity, back to the dot, back to the cavity. I should see this Rabi oscillations. Unfortunately, that is a very difficult experiment for us to do for 2 reasons. One is we're using picosecond pulses from a mode-locked laser. It's very difficult to shape the pulses to continually increase the pulse duration in a nice way. The second is that simply if we make the pulse, if we go from the amplitude, the lifetime of the photon in the cavity is about 12 picoseconds. If we increase the pulse duration much beyond 12 picoseconds, we start to become incoherent. So there's another way to do this, which is more simpler for us, instead of tuning the amount of time that the dot spends in the cavity, we tune the Rabi frequency. And how do you tune the Rabi frequency? You can increase, the Rabi frequency is a function of both the coupling strength and the detuning between the dot and the cavity. So we simply increase the detuning between the dot and the cavity, and that detuning is proportional to the power of the laser because we're using a Stark shift to tune the dot. So as we increase the Stark shift, we tune the dot further and further away from resonance with the cavity. And when we look at the cavity emission and the dot emission, we see now this Rabi oscillation that is 90 degrees out of phase, where you can see the signature of the pi, 2 pi, and 3 pi pulses. We're decaying very, very fast, and there's other incoherent processes that start to decohere us, but we're actually able to observe this coherent transfer. Okay, so in the last few, how much time do I have? Probably only a few minutes. Yeah. Okay, so perfect. So in the last few minutes that we've confirmed I have, let me talk about a few future directions. Kai did a really good job of describing some of the real interesting aspects of working in this kind of all solid state system. We have a really opportunity to look at a platform for integrated quantum photonics where we put everything on a chip. In the Vukovic group, they showed ways to do wave-guided devices. Later on, we actually were able to observe strong coupling with these kind of devices. So we really have ways of instead of shining light off the surface of the chip, use integrated waveguide cavity structures where we can start to scale these things up and connect different cavities with waveguides. As was mentioned in the previous talk, there's now a lot of work on integrating detectors as well as heaters and tuning elements so that we can have all of our elements, our emitters, our optics, and our detectors on a chip. And then we can start to dream about putting many, many of these on a chip. But whenever you do that, you're going to run into two difficult problems. The first one, which is obvious just from looking at what these samples look like, is that the dots are randomly dispersed on the surface. And so if I just want one dot, that's no problem. I just hunt and find a dot. But if I want 5 cavities and a dot in each individual cavity, I need to put them in the right places. Turns out that is pretty much a solved problem for the most part. There's been many works that have shown regulated growth of quantum dots, and they've become quite good. Recently, in the lab at the Naval Research Laboratories, Dan Gammon's group, they've been able to show regulated growth of quantum dots with line widths that are not much different than the line widths we see in self-assembled dots. So this problem there's a known solution for. But still, even if you do this, there's probably a much more insidious problem that you have to face, and that is that not only are we dealing with spatial randomness, we're also dealing with spectral randomness. Each one of these dots has a slightly different shape, size, and so when you look at the ensemble, they all have different energies, and if I want 5 cavities and I want the 5 dots to all interact with each other, they all have to have the same frequency, and there's no real foreseeable way to solve this without adding some sort of tunability to the dot. A while ago, we showed kind of what I would call a hack or a kind of a cheat, where we could kind of get two dots coupled to a cavity. So maybe that's a nice way to go from 1 dot to 2 dot experiments. We exploited the fact that a Zeeman shift, you have a red shifted and a blue shifted branch, and at the right magnetic field, you can actually get 2 dots to match each other. And we indeed showed that we can simultaneously couple them to a single cavity, but it's not scalable. We can do 2 dots, but then we're stuck. In order to go beyond 2 dots, we need some sort of tuning knob. I mean, I think it's something like when the circuit QED people spoke earlier today, they mentioned how well they can tune the resonances, the frequencies of the dots relative to each other, relative to the cavity. We need something like that. One thing that is very compelling idea to us is to use strain, because it's been shown that strain can actually tune a dot over the entire inhomogeneous line width. So that means we could tune any one dot into any other dot on the chip. This was done, however, just where the entire sample was strained, so you didn't have individual dot tunability. To do this with a chip-integrated device, you would have to be able to apply local strain. One of the things we're interested in is perhaps using the piezoelectric properties of gallium arsenide itself. But just as a proof of concept, we've actually shown that the strain tuning does work. It does allow us to tune a quantum dot onto a photonic crystal cavity. We were able to tune a dot onto a cavity and observe this strong anti-crossing. We were only able to get 1 MeV of tuning as opposed to the 20 MeV that was demonstrated previously, presumably because we did not do as good of a job of transferring the strain onto the wafer as these guys who are real experts at it and us who are not such experts. But it does show that this is kind of one possible way to do it. Other people have been looking at photooxidation as another way to do it. But this is a really important problem. I think this is kind of the challenge that we're all going to have to really seriously address to move ahead. Okay, so I want to finish by thanking the people that actually did the work, my graduate students, in particular Tao Kai and Shuo Sun, who did a lot of the measurements you saw today, as well as my former postdocs, Ranajoy Bose and Hyo-Chul Kim, and also Glenn Solomon, my collaborator at the Joint Quantum Institute, who grows all our MBE wafers. And I want to also thank you for your attention and encourage you to ask questions. Thank you.
Thanks, Edo. Are there any questions?
So I guess, a lot of these things were the gates, so it was post-selected. So wasn't it, you condition on getting a photon out for some of it.
When you're saying the gate was which post-selected gate?
When you send on, and then, you also when you do the rotation of the polarization, and when you switch the Ramsey, right, it's post-select. It is, you need to condition getting a photon out.
Condition, when you say post-selected, okay, so what we do, okay, so the device efficiency is very low. In other words, so I wouldn't call it post-selected because we don't have to post-select. There's a difference between that and post-selection. But yes, the device efficiency is very, very small. We use actually a spatial, we use a spatial filter to eliminate all the photons that didn't couple to the cavity. And so what that ends up giving you is a device that has very high contrast. You don't have to post-select on anything, but most of the time your photon is lost. So the efficiency, and it's very, it is an important question, especially when you're working off chip, how to couple light in and out efficiently. One would hope that if you went to kind of a more planar integrated architecture, those problems become much easier.
These charge qubits, so you mentioned the two different ways that you can tune them, magnetic and strain. Doesn't electric field also have an effect?
Yes, it does, and that's a reasonable way to tune it. The problem with electric field is that when you apply, it works up to a point. Then when you increase the electric field, you separate the electron and hole wave function. And then the oscillator strength of the dot dies. And so it doesn't emit anymore.
But then in the piezoelectric material, if you have strain, you also have electric field.
Right, so the question is, what is the dominant reason why your dot is shifting? Is it because the lattice of the quantum dot is being constrained? Or is it because you're creating a large electric field? And so I guess it's presumably the latter, because when they tune the dot with strain over 20 MeV, they don't see any reduction in the fluorescence efficiency of the dot. So presumably whatever electric field you've built up is not separating the electron and hole wave function. It's really just you're pressing the dot, and you're shrinking the size of the dot, but you're doing it symmetrically and not giving the electron and hole any preferences to go to one side of the dot versus the other.
So in this example where you said about creating these more complicated wave functions with higher photon states, if your losses are so bad, is there any chance of actually seeing these states, or is there?
With these cavity QED parameters, the ones that I showed, no, there's no chance of seeing these higher order states. With the best cavity QED parameters that have been observed in quantum dots, there is hope. But with the device that we showed here, no, it's too lossy.
If there's no more questions, let's thank you again.